Thank you so much. Thank you so much for the invitation. For many people, my generation, Grenoble is a very special place. For me personally, a visit to Grenoble as a guest of Demailly and Bonavero was my first serious time abroad. I learned a lot of mathematics here, and I also learned the word solidarity strike, which I had never known before. Thank you. So to start today's talk, let me recall a very classical theorem that has a long history, which I'm not going to get into. The decomposition of manifolds with vanishing first Chern class. So theorem X compact Kähler manifold C1 of X equals 0, then there exists an étale cover of X by product of a times yi times zj, where yi are irreducible, holomorphic, symplectic, and zj are Calabi-Yau. And by irreducible, holomorphic, symplectic, I mean simply connected, and on each piece there is a two form that generates any other form. So this is one connected, exists a two form that generates any other form. And by Calabi-Yau, I mean simply connected and no forms at all, except if you wish a zero form, the constant function 1, and a top form. So one connected and no forms. This is, of course, a very classical and very important result. However, if you're grown up in birational geometry like I am, you might wonder whether it's possible to extend this result to the class of all varieties with Kodaira dimension 0. The fundamental invariant in birational geometry is the Kodaira dimension, and the minimal model predicts, the minimal model program predicts that if you start with any variety that has Kodaira dimension 0, then after finitely many contractions and flips, you should end up with a variety whose first Chern class is 0, but of course you got to pay a price. These spaces will be singular. So we started to wonder about singular spaces with first Chern class 0 a while ago, and the first result that we could come up, so aim generalize to singular spaces. So the first result that we came up does not exactly decompose the variety. Instead, what we found was that there is always a canonical decomposition of the tangent sheaf. Like here, obviously, this decomposition into factors induces a direct sum structure on the tangent sheaf. And what we could do in the general singular case is we could recover this decomposition of the tangent sheaf. So theorem, and that was joined with Daniel Greb and Thomas Peternel, is say X a canonical variety, Kx is numerically trivial to 0, then there exists a quasi-étale cover of X by, again, n abelian times z to x such that first thing is the irregularity of z equals 0. Second thing is that Tz is a direct sum where all summands are stable with respect to any polarization. By stable, I mean slope stable with respect to any polarization, and closed Lie bracket. So Lie closed stable with respect to any polarization. A little more is true. In fact, this stability remains invariant even if I pass to further quasi-étale covers. Usually when I have an étale or quasi-étale cover, pullback of stable is semi-stable, but we claim that this stability of the summands here is retained after further covers. Quasi-étale, maybe I should briefly mention, is étale away from the singular locus. So we are dealing with branched covers where the branch locus is small and it's contained in the singular locus, if it's branched at all. Right. The method to prove this is essentially Bogomolov's old ideas translated to the setting of canonical singularities with like space-age technology. We are able to make the old idea of Bogomolov fly in the singular setting by constructing a duality pairing for reflexive differential forms. But I would rather not go into details. Instead, there's the obvious question. We found a decomposition of the tangent sheaf. The tangent sheaf is a direct sum of foliations. Now, does that decompose the manifold? And the answer is, of course, in general, we don't know. However, there's been progress lately. So, question now, does that decompose X? Maybe after further quasi-étale cover or étale cover, who knows? One answer was given by Druel last year. The answer is yes if the dimension is no more than 6. So if you look in his paper, he deals, I think his result is formulated for dimension no more than 5, but the methods, I think, carry a little further. So yes, if the dimension is no more than 6. There's another partial answer given by Druel and Genanscha this year. Yes, if the singularities of X are smoothable. So answer is Druel, Genanscha. So yes, if the singularities of X are smoothable. So, okay, we don't know the answer in general, but at least it's conceivable that some more results in this direction should hold. And obviously, no matter how a structure theory for varieties of Kodaira dimension 0 might eventually turn out in the future, it's at least conceivable, or I would think plausible, to see that those varieties that come out of the decomposition, that those varieties where the direct sum structure here has only one summand, so the tangent sheaf is stable with respect to any polarization, this will be an important, say, building block in any structure theory of varieties of Kodaira dimension 0. So singular spaces, first Chern class 0, tension sheaf stable and remains stable under further quasi-étale covers and irregularity 0. So, and the aim today is to explain a new, if you wish, approach to this decomposition and to try to understand those, let me call them, building block varieties out of, hopefully, eventually, any other variety of Kodaira dimension 0 is constructed of. So, in particular, I would like to argue that the fundamental dichotomy that we know from the smooth case, namely there is irreducible holomorphic symplectic on one side and Calabi-Yau on the other, that fundamental dichotomy also carries over to the singular setting. So there's exactly two flavors of building block varieties. So aim. So analyze the setting and describe varieties with Tx strongly stable. So the setting for the rest of the talk, I would like to consider X a projective variety that has no worse than KLT singularities, and the canonical class is numerically trivial. So by Kawamata and Nakayama, we know that the canonical class actually becomes linearly trivial after passing to a suitable quasi-étale cover. Right, I also want to fix throughout an ample divisor. And then, of course, the most important tool in our analysis is the singular Kähler-Einstein metric that was constructed by Essidieu, Getsch, and Seriai. So let omega h be the associated singular Kähler-Einstein metric, which on the smooth locus of X defines an honest metric without any singularities. So, and of course, the main player in the game is, as it was in the smooth case, the holonomy. So this is maybe the second paragraph of my talk, holonomy. So we fix a smooth point of our manifold, and we look at G, which is the holonomy of the smooth locus with respect to this metric. And then, of course, we have the restricted holonomy, so the maximally connected subgroup in there. So G naught is x rec omega h x naught. So this is restricted holonomy. And we would like to understand the two. Obviously, maybe don't put your hopes too high. So the first thing we realized in this context that X rec is, of course, a non-compact manifold. And this non-compact manifold, X rec, can never, ever be geodesically complete. So this is a theorem. As long as you have one single singularity, this thing is never geodesically complete. So there's certainly no de Rham composition, and words like Chiga Gromol become very complicated in this setting. Note XREC is never complete. Yet, of course, we do have the methods of Berger-Simons. We have the classification of restricted holonomy, which is usually formulated in the textbooks as a classification of holonomy for complete or even simply connected manifolds, but then the proof is much more general, and the Berger classification even applies to arbitrary manifolds. So let me talk a bit about the restricted holonomy first, and then we can see what we can say about the holonomy in general. So as to restricted holonomy, as for G0, we know, and here I should write Berger-Simons, that locally near our smooth point X, the manifold has a product structure. It decomposes as a product of irreducible Kähler manifolds. So X decomposes as product of irreducible Kähler manifolds. Let me be a little stroppy and write X is X0 times X1 times Xk, with the understanding that this is wrong as stated. This is a decomposition that takes place in the neighborhood of X and not globally. And the restricted holonomy has an appropriate decomposition as well. So restricted holonomy decomposes as G0 is H1 times Hk, where every factor Hi acts irreducibly on the tangent space of Xi and trivially on the other summons. So maybe I should then decompose the tangent space as well. So this is Txk. Right. So where Hk acts irreducibly on Txk and trivially on the other summons. And the Berger classification applies to these HKs. The HKs must be groups in Berger's list. So there's essentially a finite number of possibilities. Of course, the factors here, they still carry Ricci-flat Kähler-Einstein metrics, which by classical analysis and going through the list leaves us with only two possibilities for these groups. Namely, they must be either SU or SP. So Berger's classification implies that HK is SU or SP, and this is of course where the dichotomy of Calabi-Yau and irreducible holomorphic symplectic comes from. So in a sense, this is a complete answer to our questions, what is the restricted holonomy and can we understand the restricted holonomy? But then, of course, I'd like to derive global statements, so I really need to understand the holonomy. So now what about the holonomy? Of course, we know that the restricted holonomy inside the full holonomy group, this is normal. So the holonomy group needs to send g orbits to g orbits, and that means the holonomy group needs to stabilize this summand, and the other summands perhaps get permuted. So we have g by g naught permutes the numbers between 1 and k, and of course, by definition of restricted holonomy, we have a section from the fundamental group. So that tells us that after a finite étale cover of the smooth locus, we can just as well assume that the permutations are trivial. So that means the holonomy group actually stabilizes every summand here. So it might act in a highly non-trivial way on this summand, and the other summands get stabilized. So we have an étale cover of the locus, or in other words, we have a quasi-étale cover of our total singular space. So that means after quasi-étale cover can assume that permutations are trivial. So this is maybe star. So a G action, the G action stabilizes the decomposition star. Okay, so what have we won? So we have found in our tangent sheaf now globally a summand that is flat, and then with the other summands maybe we are not so sure at this point. And this is where methods of Stéphane Druel come in, building on amazing results of Bost. He has shown that this flat summand after further quasi-étale cover splits off and gives me the abelian part in the decomposition. So Druel, building on results of Bost, Druel, Bost have shown, so the flat part splits off and gives an abelian factor. So we can maybe assume from the outset, let's assume that there is no abelian factor. We have split off everything we can. Of course, there is classical work of Kawamata who says that if the irregularity of our space is positive, then an abelian part will also split off. So splitting off everything we can we can assume that there is no flat part, and we can assume that the irregularity is 0 and remains 0 even after I pass it to further quasi-étale covers. So Kawamata says Q of x positive, then torus splits off. So as a bottom line, I can assume that irregularity is 0 and nothing abelian will ever split off. Oh, this is so a summary. I can assume the factor, what was that? Tx naught is trivial, and Q of x equals 0. And that remains true under further quasi-étale covers. Now, how does that help me to get a handle on the holonomy group as opposed to the restricted holonomy group? So this is extremely useful. Let me write, this is cool because the holonomy group, the restricted holonomy group, is normal in the holonomy group. So if I look for the holonomy group and I ask myself what possibilities are there, obviously I have to look at the normalizer of the restricted holonomy group. But the restricted holonomy group, we know, is a product of SU and SP. The holonomy group respects that product structure, stabilizes the decomposition. So if I look for the holonomy group, I don't just have to look at the normalizer of G naught. Instead, I have to look at the normalizer of SU, the normalizer of SP, the normalizer of SU again. And if you ask me what the normalizer of SP is, the answer is I don't really know, but it's written in Dess's book. So, so this is cool because we know. So G is in the normalizer of H1 times normalizer of H2 times normalizer of HK. And we know precisely what these groups are. So the classification tells us G by G naught, after all these simplifications, is abelian. So that comes out of the classification. And why is this a good thing to know? Because the irregularity is 0. We are dealing with singular spaces, but the singularities are just KLT. So what you're used to from the world of smooth manifolds is still true. The irregularity 0 implies that the fundamental group, the abelianization of the fundamental group, has rank 0, so maybe finite, and surjects onto the abelian group G by G naught. So So we have pi 1 of x surjects into g by g naught, but this is abelian. And that factorizes via the abelianization of pi 1, which is finite because the irregularity is 0. And because we understand the singularities of the minimum model program enough, so we see that the relation between irregularity and topological cohomology still works. So that means that the fundamental group might possibly be infinite. So we are in a much worse situation than what we have in the smooth case, where after splitting off the abelian part, the fundamental group becomes finite. It might be infinite, yet we know that there is a finite cover that makes the difference between restricted holonomy and holonomy goes away. So after finite étale cover, we can assume that restricted holonomy equals holonomy, and we have classified precisely what can possibly come out. So after finite cover, can assume that G is equal to G naught, and this is a product of SU and SP. So this is essentially what I wanted to say about the holonomy of these singular spaces. Now, of course, what is the holonomy good for? The holonomy is essentially important because there's the Bochner principle. A tensor or differential form is holomorphic if and only if it's parallel. And so this is the second part of my talk, Bochner principles. So this is section 2. And let me start out with the main theorem right away. So in our setting AC infinity section of omega 1 x reg to some tensor power times t x reg to some other tensor power is holomorphic if and only if parallel. About the proof, I'm going to say next to nothing. We're coming to the borders of my expertise, I should say. I mean, the classical Bochner principle is proved by integration by parts. So if you wish a Stokes formula, now, of course, we have a space that is no longer compact. So all this becomes so much more interesting. And what's required now is a detailed analysis and understanding of the behavior of the singular Kähler-Einstein matrix as we approach the singularities. And this is, of course, where Henri's expertise comes in. So among the three of us, he understands these matters perfectly and was able to make the analysis fly, so to give us this result. So instead of getting lost in estimates of analysis, let me instead point out a few applications now. So what is this good for? Of course, you can say what we have now is we have, if you wish, a perfect understanding of what tensors there are on our manifold, on the smooth locus, the non-compact smooth locus of our manifold, because the tensors are precisely dictated by the representational theory of SU or SP, and if I don't understand this, then Daniel Greb does. So we know precisely the answer is representational theory tells us exactly what tensor fields there are. So why is this maybe interesting? One remark is application 1 or application 0, if you like. You can reconstruct the holonomy group by looking at the holomorphic data, what tensors you have. If and only if. These are two Fs. Thanks. So you can reconstruct the holonomy group by looking at what holomorphic tensors you have. So I don't know, maybe this is obvious to Philippe, but to me it's not. We started with a singular Kähler-Einstein metric, and the singular Kähler-Einstein metric depends heavily on the choice of an ample bundle. You choose another bundle, you get a different metric. I mean, it must be different because its cohomology class is different. Yet, what we can see is the holomorphic data dictates what the holonomy group is. So the holonomy group is independent of the choices that we made at the very beginning. So application one is holonomy is independent of chosen ample class H and associated metric omega H. So the holonomy, if you wish, is something, or the isomorphism class of the holonomy, I should say, is something that's intrinsic to our singular space and doesn't depend on the choice. And then, of course, you can ask, how does it behave under elementary operations surgery? So for instance, something that I have been sweeping under the rug all the time is the singular Kähler-Einstein metric is extremely well behaved under quasi-étale covers. It satisfies the universal property under quasi-étale covers, so the pullback is right. Is not so clear to me what its behavior is, for instance, in settings where I have a small resolution of singularities. And with this, you start with a variety that has first Chern class 0. You take a small resolution of singularities, or maybe a Krappendt resolution, or a partial Krappendt resolution. And then you change your metric. Upstairs, you will have to change a new ample bundle. And you can ask yourself, how does the holonomy behave under these surgery operations of birational geometry? And the answer is the holonomy does change in interesting ways which we do not yet fully understand. So it's clear from elementary examples that something is going on. The holonomy does change in non-trivial ways, but I still have to figure out some inequalities there, what can actually happen. So that brings us to question, how does holonomy behave under, say, Crepin resolution. Or you could ask for like the smallest partial resolution of singularities that doesn't change the holonomy. I don't know. Right. Then there's further applications. There's something we can say about the fundamental group. And this goes back to works of Campana, who relates in this setting the fundamental group to the holomorphic Euler characteristic. Essentially, the result is if the holomorphic Euler characteristic is non-zero, then the fundamental group must be finite. Now, the holomorphic Euler characteristic, you have hi of the structure sheaf. And if you were on a smooth space, you would know that this is a statement about existence of differential forms. Now, in our singular setting, we understand the singularities of the minimal model program well enough, so we can also relate the cohomology of the structure sheaf to the existence or non-existence of tensors that are defined on the smooth locus only. So that statement here, the Bochner principle, if you wish, implies also a statement about holomorphic Euler characteristic, and therefore, in good cases, even dimensional cases, about the fundamental group. So this is application 2. So Campana relates finiteness of pi1 to topological Euler characteristic, but the holomorphic Euler characteristic can be expressed in terms of tensors. So we get finiteness in a number of cases. Including that where G has only one factor and is SP. There's another application in a similar vein. This goes back to a fairly recent work of Brunbarb, Klingler, Totaro. Brunbarb, Klingler, Totaro relate the fundamental group to a symmetric sections in symmetric products here. But of course, we understand those as well. So Brunbarb, Klingler, Totaro relate the fundamental group and some properties of it to the existence of symmetric tensors, and we have complete control over what can possibly happen. So a consequence is that their theorem applies in our setting and gives us not exactly finiteness of the fundamental group, but it tells us that there is almost no finite dimensional representation over any field with infinite image. And it also tells us something about the weakly polynomial growth of the fundamental group in the sense of Gromov. So now I need to clean some. I guess the Bochner principle has to die now. Here. So, right, application free Grünbarb, Klingler, Totaro, relate pi1 to symmetric forms. And let me spare you the precise, yep. Oh yeah, of course. There's many things I have to sweep under the rug. Obviously, we know from work of Takayama that the fundamental group doesn't change under resolution of singularities. So that can be used in order to reduce ourselves to the, but you're certainly right. There's more work behind this, which makes the paper eventually rather long. To symmetric forms, so we get severe restrictions for pi1. Personally, I find this weakly polynomial growth business in the sense of Gromov maybe the most interesting here. And then we're coming to the end of my talk, and maybe the most important application of them all, which is extremely dear to Daniel, so I shouldn't forget to mention this. And since I have only 1 minute left, let me be very imprecise at this stage. So maybe the most important application is so double underline. We think with this business in place, we have found the correct definition of irreducible, holomorphic, symplectic, and Calabi-Yau. So we have correct definition of Calabi-Yau and IHS for singular spaces. In particular, irreducible holomorphic symplectic spaces are simply connected. We can't say that about the Calabi-Yau part. And in particular, their main characterization is the existence of a 2 form on the smooth locus that generates any other form, and no form on this side of the picture. And most important of them all, we recover the fundamental dichotomy between Calabi-Yau and irreducible holomorphic symplectic also in the singular setting. Thank you for your time.